Hello and welcome to Physics Video Optics.8, Diffraction Gratings and Spectrometers. In this video we will discuss what happens when light goes through multiple slits rather than just a single slit or a double slit situation that we've already discussed. And we will look at applications where this is used. Unlike single and double slits that we've already talked about, diffraction gratings can have hundreds or even thousands of slits per centimeter. And when we talk about a diffraction grating, we are talking about having a large number of equally spaced narrow slits or lines. So if this is our slide, remember we started with a single slit and then we had double slits, but now we're really talking about having hundreds and hundreds and hundreds of equally spaced parallel lines on a diffraction grating. The more the lines or slits there are, the narrower the peaks. So we have just a few slits here in A, and you can see that there are lots of peaks, the central maximum at m equals 0, and then the next maxima, the first order maxima at m equals 1 and m equals 2, but they're pretty wide. This right one, the width of the peaks is considerably thinner, which means that there are more lines on the diffraction grating on the right in B than there are in A. This also means that the peaks of B are more defined and more easily visible, as well as being more measurable as to where the center of that peak actually is. This is especially true when you compare diffraction gratings to double slits, but it is also very important to realize that this occurs when we have diffraction gratings as well with different number of slits or lines on them. There are really two different types of diffraction gratings. One is called a transmission grating, which would be like a slide like I've drawn here, where there are slits drawn in the slide. The other one is called a refraction grating, and the refraction grating has lines that are carved into a reflective surface, like a mirror. So the reflective surface of the mirror has lines carved into it, and then rather than going through, it reflects off as if it were going through. If we look again at how light goes through a grating, similar to what we did with the double slits, we can see that it also looks very similar. The separation between the slits is still d. The difference in distances that each ray needs to travel is still delta L, as shown on the picture here. And now delta L, as it did before, is equal to d sine theta, d being the distance between the slits, theta being the angle that the light bends at. Oftentimes we are not actually told the distance between the slits, so we're not given d. Instead, we're told how many lines are drawn per centimeter on the grating. For example, you might be told that there are 500 lines per centimeter. And what you need is d, so you need to get d out of that information. All you really need to do is invert, because d is going to be the number of centimeters per line that you have. So d will be equal to 1 over 500. And then you can use this value of 1 over 500 to put into your equation. Now, also remember that if we are looking for the maxima on the screen, similar to the double slit diffraction that we were talking about, then delta L, which is equal to d sine theta, is also, if we want it to be a bright spot, going to be equal to m lambda. This will give us our maxima. So lots of similarities between double slit and diffraction gratings. However, there are some differences. So again, we have the equation written up top here, rearranged slightly to find out what the angle is of the light difference from the central maxima, how far out it is. This top picture here is illustrating what happens if you have two different frequencies of light going through the grating at the same time. We still get a central maxima at m equals 0. Notice it's shown as being white. Then the next at m equals 1 and m equals 2. However, since there are two different wavelengths of light, they will spread out differently, and you will get a series of alternating colored lines with each color having a different location for each maxima. So the blue light, having a wavelength of 400 nanometers, has M1 closer and M2 closer than the red light with a wavelength of 700 nanometers. So you can see here that the angle of diffraction is significantly different between those two wavelengths. If we put white light through the diffraction grating, you can see the same thing occur. But now, with all of the different wavelengths of light spreading out, we don't just get strip or strip, we get a full rainbow. Note that each maxima gets dimmer as we go away from the central bright one. We have the central bright, there would be no dispersion, so you would get a white light, and then we would get a rainbow at m equals 1. Now notice m equals 2 is going to be significantly fainter, and it's going to also be spread out more because of that. We can use the brightness of the first order maxima as well as of the central maxima to make measurements of locations and wavelengths of light. The device that we use to make such measurements is called a spectrometer. The science of making measurements with a spectrometer is called spectroscopy, and I'm sure you've heard that at some point in time. A spectrometer makes very accurate measurements of wavelengths using a diffraction grating or a prism. So we have the light source here on the left, and chances are the light source is going to be emitting light in all sorts of different directions. We only want light to be headed in parallel to the grating. So we have to first put the light through a slit, which is labeled S here, which is called a collimator. And the collimator is not a super thin slit because we don't want the light to disperse yet. We just want it all to be coming in parallel to each other. Then what happens is light comes out of the collimator and goes through our diffraction grating some distance L away. It will then bend away from the center line, and you then will look with your eye through this movable telescope that can rotate around the axis of the spectrometer. You move the telescope around till you find the bright spot, and from there, there's usually a scale on the outside of the table that allows you to measure the angle. You can then use this incredibly accurate measurement to determine the wavelength of light, which is super cool if you have a source that you don't know what it is that you're looking at, and you will have a couple of guesses because of its color. You can find out not only a more definitive number for the color, but you can also find out its exact wavelength. Sometimes these devices do not actually use diffraction gratings because they're pretty hard to make, but oftentimes instead of a diffraction grating, they will have a diffraction reflector. So they'll put a flat mirrored surface there instead of a slide and scrape lines into the mirror, and then you look for the reflected rays rather than the transmitted rays. And when that occurs, your telescope needs to be over in this position rather than over there, but that's okay because it'll still work, and then you just measure this angle down for theta rather than down from the back. These devices are used a lot in astronomy because it allows us to see what types of elements are in the stars and the planets that we are looking at, because we can look at the light that comes in and then we can figure out where the different angles are coming. So for example, if we take a look at white light, similar to what comes from the sun, we would get a continuous spectrum, the rainbow as we know of it. But if we were to take a tube filled with, say, hydrogen gas and send electricity through that, the atoms of hydrogen would have their electrons get excited, and then those electrons would start to glow. And in that glowing, they would jump down back to their regular normal state rather than being excited. And in doing so, they would emit light. And hydrogen, you have a violet, a blue, and a red light emitted. Helium, you've got similar colors on the end, but much different. Look down here at nitrogen. Nitrogen has lots and lots of spectral lines that are shown. Mercury has just a few, the purple, the green, and the yellow. And then carbon monoxide has almost a continuous spectrum, but you can see that there are spots that are significantly more distinct than others. So the cool thing about spectroscopy is that you can not only look at elements and individual atoms or individual samples of atoms to see what the spectral lines look like, but you can also look at molecules, which means that we could use this to see if there might be water in an atmosphere on a distant planet, because we could get the light that's being reflected off of the atmosphere and see what the spectral lines are from it, and then from there we could identify what molecules are there. The reason that these different elements each have distinct sets of lines has to do with how electrons react with photons coming into the atom. If you remember your chemistry sum, then you will remember what I'm talking about here. But just in case, let's review for a sec. Remember that electrons can only exist in certain spaces within the atom, within the electron cloud. According to Bohr's model of the atom, electrons can jump between those spaces or energy levels, but cannot exist in between them. So we have energy level 1 here, real close to the nucleus, then 2, 3, 4, 5, 6. It could continue out if we had a really large element, but for the moment, let's just look at these. So electrons can exist on any one of these different colored energy shells, but they cannot exist, say, here in between. So if you have an electron that has a lot of energy and it becomes in an excited state, it might jump out up here to level 5. And then as the atom calms down some, that electron wants to jump back in to its normal state. If it jumps from 5 to 2, then it will emit photons or energy packets at wavelengths of 434 nanometers, which for us is violet. If it jumps from a 4 to a 2, then it emits blue-green color at 486 nanometers. If it goes from 3 to 2, it will emit a much larger wavelength of 657 nanometers in red. So as each atom's electron at different energy levels jumps from one energy level to the other, it emits or it absorbs particular amounts of energy. And the amount of energy that it emits or absorbs is going to be directly related to the colors that are emitted or absorbed by the atom. And that's what we can see in a spectroscope. Here, this picture is showing in particular the wavelengths of light that are emitted when electrons jump down from their excited state to their normal energy level. So whatever atom this happens to be, you would see a bright line of violet, of blue-green, and of red at those wavelengths. If this was what we were looking at from light coming from a star, we could then go back and look at the spectral lines from each individual atom and determine what atom this star, or what atoms this star is producing. Okay, let's do a couple of quick problems. A 2500 line per centimeter grating produces a third order fringe at a 36.0 degree angle. What is the wavelength of light that is being used? Okay, well, remember that we're going to start with the equation. D sine theta equals m lambda. We know that theta is 36.0 degrees. We know m is third order, so it's 3. We don't know what lambda is, but we do know that d is 1 over 2500 lines per centimeter, which means then that d is 0.0004 centimeters. All right, I'm looking for lambda. So lambda is equal to d sine theta over m, which is 0.0004 times the sine of 36 all over 3. This turns out to be 7.84 times 10 to the negative 5 centimeters. We don't typically leave lambdas in terms of centimeters, especially not when we're talking about light. So if we change this to meters, it is 7.84 times 10 to the negative 7 meters. However, again, since it is light, we typically refer to it in terms of nanometers. So we say, aha, the light that did this has a wavelength of 784 nanometers. One more. A diffraction grating has 500 lines per millimeter. Find the angular spread in the second order spectrum between green light of wavelength 550 nanometers and blue light of wavelength 450 nanometers. So the angular spread, remember back to the beginning of the video when I showed you the picture of the red and the blue light where they each had their different spacing between M1 and M2 maxima. So here I want to know, what is that spacing in fact? So by angular spread, we are really looking for what is the difference in the angles between the second order maxima of green light with a lambda of 550 nanometers and blue light with a lambda of 450 nanometers. Our D we can get from this 500 lines per millimeter. We can end up getting D from there. Notice that none of these are in the same units for distance, so we'll need to watch that. We're going to start again with D sine theta equals m lambda. In this case, I'm looking for angular spread, so I want to know theta. Theta is equal to sine inverse of m lambda over d. 500 lines per millimeter is able to be converted to d being 1 over 500,000 meters. All right, so let's figure out theta for blue. It'll be sine inverse of 2, because m is 2, times 450 times 10 to the negative 9 meters, divided by d, which is 1 over 500,000, which becomes sine inverse of 0.45, which leads to the angle of the second order spectrum for blue to be at 26.74 degrees. Do something similar with the green. And we get sine inverse of 2 times 550 times 10 to the negative 9 over 500,000. Sorry, over 1 over 500,000. And that becomes sine inverse of 0.55. So the angular placement of the second order maximum for green is at 33.37 degrees. So the angular spread, the difference between those, is 33.37 minus 26.74, which turns out to be 6.63 degrees. Now, the reason that we can find this and that we are interested in this is because not only are the colors that show up in a spectral line important in terms of determining what the element or compound is that we're looking at, but also the spacing between those lines is part of that fingerprint of the spectral signature that the different elements and molecules give us. So if we can figure out this angular spread as well as knowing what colors were coming out, we can precisely determine what type of elements are in stars. So with this, we should be able to go on and continue solving problems. Bye for now.